So now let's consider some general lower bound on the extremal number, not lower bound, okay. So before that, we have proved this Ehrlich-Stone-Simonovich, which determines, roughly determine the extremal number of given graph f. However, one catch is that here, if the chromatic number of f is 2, meaning that this is bipartite graph, then this entire part becomes 0. This only gives you that bound is subquadratic, which doesn't really determine the asymptotic of this. So for bipartite problem, we call it a degenerate case of, Turan problem, or degenerate Turan problem, or degenerate extremal problem. It's to determine the extremal number of bipartite graph. So we have to deal with them in a, ad hoc way. There are no one theorem which tells you the extremal number of bipartite graphs. So one of the things that we learned in the undergraduate graph theory is when ST are given, we have the extremal number of KST is at most n to the 2 minus 1 over s times some constant. And we don't know whether this is tight for all, most of the S and T. But we do know that this is tight for several values. One of them is that we know that this is tight for, when I say this is tight, I mean the exponent. We know that if S is 2 or 3, then these are tight. And also if T is at least S minus 1 factorial from plus 1, so T is much bigger than S, then it is tight. But most of the case, it's, we don't know whether they are tight. Meaning that we don't know the lower bound, meaning that we have to find the construction. So in order to prove a lower bound on the extremal number, we have to find the construction. If we want to say this is at least certain number, then we want to find the construction which has roughly this many edges, having no copy of KST. So to get some lower bound, there are several techniques. One of them is using the randomness. So by using probability method, we can actually find some lower bound, which is, which may not be tight, but at least give us some lower bound. Let's say 2 density over graph H as a maximum of over all subgraph H prime, where this H prime has at least 3 vertices. You take the number of edges in H prime and you subtract by 1, and you count the number of vertices in H prime and you subtract by 2 and then divide. And this quantity has some meaning, and you will see the meaning of it in the following theorem. For any graph f with at least 2 edges, there exists a constant C such that for any n there exists an F-free graph which contains no copy of F on n vertices with at least C times n to the 2 minus 2 density of F edges. In other words, extremal number of F is omega of n to the 2 minus 2 density of F. So we use probability method. More specifically, we use alteration method. So first we can assume that n is large because we only want to find one constant. So if we choose this quite small, then for any small n, I mean this number could be very small, could be smaller than 1. So if we choose this C very small, let's say 0.001, then we can automatically assume that n is at least 100. If this is 1 over 10 to the 10, then we can assume that n is at least 10 to the 5. Otherwise, I mean, this would be less than 1 and the statement is trivial. So we can assume that the n is large. Consider a random graph, G and P, on vertex set bracket n with P being, say, half times n to the minus 2 density of F. And let F prime be a subgraph of F with, which achieves the 2 density of F. So now let X be the number of edges in this G and P, which is a random variable, and Y be the number of distinct copies of F prime in G and P. Then by linearity of expectation, what we know is that if you subtract Y from X, then that's same as expectation of X minus expectation of Y. And each edge is included with probability P. So this is P times n choose 2. And what's the expectation of Y? You choose n vertices. And this will, contains a copy of F prime with probability P times E of F prime. And this will actually overcount things up to the automorphism of F prime. So this actually gives us the expectation of Y. So for example, if Y is, F is this graph, P3, then you choose 3 vertices, I, J, K, and then probability P, there is an edge, then you count this F by 1. This contributes to Y, this contributes to Y by 1. And we divide by this number of automorphism of F prime, because this is counted by when we choose K, J, I, and then probability P, there is an edge. Then this also counts this case. And for the case where all three of them are there, then you count this one, this one, this one. So this actually contribute to y by 3. So this formula actually is the expectation of y. Then this is by our choice. This is half times so quarter times n minus 1 times m n to the negative 2 density of f minus, this is at most this. Then what's this? This is 4, let's say this is 5, at least 1 over 5 to the n to the 2 minus 2 density of f. And this is same as, we know this inequality. So what we know is and P is this. So this part is nothing but n to the minus 2 density of f times number of edges in f prime plus number of vertices in f prime. But because of this relation, give me a moment. Did I write something wrong? Oh yeah, I have written things quite long. So what I wanted to say was 1 over this. Yes. Now so this is over m to f. So sorry for the confusion. So now we can actually calculate. So we have this relationship. So that means if you take EF prime minus 1 over m to f, then that's same as f prime minus 2. So here you take a negative, then negative. This is same as 2 minus f prime, the number of f prime, plus 1 over minus 1 over m2 of f. So here you move this onto here, then this is same as 2 minus 1 over m2 of f. So from that you can actually prove that, give me a moment, this is at least 1 over 10 times n squared minus 1 over m2f. p to the e of f. It seems that I might have messed up on the constant, but by choosing the right constant, probably this has to be changed into 1/3 or 1/4. Then you can make that there is some constant here, so that you can make sure that this is actually positive. But let's just, forget about the constant for now. So we can make this constant work. Once we do that, we can actually show that this expectation of x minus y is strictly bigger than some constant times this number. So that means there exists a choice. So expectation is over some number, means that if you randomly choose it, then with some probability it could be, the result could be as good as its expectation. So that means there exists a choice such that this x minus y is at least this constant times n to the 2 minus 1/2 density of f. For such a graph, you have this graph. And every time we see a copy of f prime, we delete an edge. Then, how many edges do we have to delete? At most y edges. And there are x edges, and then the remaining edges are, have at least this many edges. We delete an edge from each copy of f prime. Then we obtain a graph with at least this constant times n to the 2 minus 1/m2f edges, having no copies of f prime, hence no copies of f. So this shows that there exists a graph with at least this many edges, having no copies of f inside of here. So that shows a lower bound on the extremal number of f. Yeah, sorry that I have messed up some numbers and some computations, but you can double check on it to make sure that this constant actually works. So okay, so next time we will learn a bit more about the other way of constructing graphs without having having specific subgraph, which give us a lower bound on the other extremal number of the other graphs.